We're now going to look at one of the great experiments in physics. You should all be familiar with diffraction patterns. If you shine a light through a small hole, like this one, or indeed if you just narrow your eyes and look at a light beam, you'll see a diffraction pattern of light and dark shaded patterns. You can also do it if you shine light through a wire mesh, a bit like this, only much smaller. And you should be aware that this is a good example of how light behaves as a wave. You should also be familiar with the Einstein idea of light behaving as a particle. And this came about from the photoelectric effect, and that's been covered in another part of the course. Now, if waves can behave as particles, why can't particles behave as waves? And this experiment is designed to set that up and show you whether particles can behave like waves. If I can show you a particle which produces a diffraction pattern, a bit like the ones you've seen before with light, then I've proved to you that electrons can behave like waves. Here's some apparatus that will help us demonstrate this. I've got an evacuated vacuum tube here with the usual fluorescent screen. And if electrons, because those are the particles we're using today, hit that screen, they will make the screen glow. Here I've got a hot wire. It is on at the moment, so it's glowing. There's a hot wire which will emit electrons. Here, just next to it, is an anode which is attracting the electrons. There's a hole in the anode, so they'll shoot through the hole at a very high speed. To get the diffraction pattern that we hope to see, we need very, very narrow slits. And we use graphite because the atoms in graphite, which look a bit like this, you can see that the spacing between the atoms are very narrow. In fact, there are only about an atom's worth between them. But if you look carefully at this, you'll find there's more than one set of slits. If I draw lines on them, you can see there are slits going in that direction, vertically, and also some slits going horizontally. And you should be able to see that the spacing between the slits, which are vertical, are different to the ones going horizontally. So I expect to get not one diffraction pattern, but two on the same screen, because there are two sets of slits. Let's see if it works. This is an EHT supply, which goes up to 4,000 volts. And this will accelerate my electrons to close to the speed of light. If I increase the PD, and you can see the PD on the scale increasing, and up to about 2,000 volts, you'll see the electrons have appeared on the screen, and there's a green glow. In fact, there's a very, very strong green glow in the middle, where many of the electrons have gone straight through the anode. If I increase the PD, you see at a value of about 5,000 volts, the diffraction pattern appears. And I have got one ring here and a second ring around there, which demonstrates the electrons are indeed behaving like waves. The inner ring is coming from the narrower slits. The outer ring is being produced by the slightly wider slits between the atoms in the carbon. If you look at the apparatus and look at what's happening, if you increase the potential difference, the rings there actually get smaller. And here are some readings taken directly from the apparatus to show that the diameter of the outer ring is decreasing as the kilovolts increase. Using these results, what I'd like you to do is to work out a relationship between the diameter of the rings and the PD across the apparatus. It's an inverse relationship, but is it a square relationship or is it square root? The teacher will help you to work this out. Have a go at it first.